Our group dropped a ball onto the classroom floor and measured its height as it bounced up and down from the floor. We used a motion detector to detect how high the ball got and how far it dropped down. We did this to measure the mechanical, kinetic, and potential energy of the ball. In doing so, we also analyzed the relationship between all three types of the energy.
This is our raw data for our energy of a bouncing ball lab. On the top graph, you can see that the time is plotted on the x-axis and the position and kinetic energy is plotted on the y-axis. The position line is the line that's above the other line, and the kinetic energy line is the one on the bottom of the graph. As you can see, the ball has bounced 5 times over the course of the lab. Now on the bottom graph, here you can see the time being plotted on the x-axis and the velocity being plotted on the y-axis. The plot shows a constant pattern with it dipping down, going into the negative velocity first, and then rebounding back up towards the detector, moving into the positive velocity direction. And it repeats until the ball stops bouncing and loses energy. Here on this slide, we calculated the initial speed. Our kinetic energy was 0.178 joules, and we plugged it into the kinetic energy formula to find the velocity. Our mass of the ball was also 0.0415, and we found that our calculated speed is 2.928. The detector measured the ball speed as 2.3, so our measurement deviated from the supposed speed that the detector obtained by about 0.6 of meters per second.
The three graphs to the right are the graphs that show the ball's potential, kinetic, and mechanical energy after each rebound off the floor. In the first graph, the mechanical energy is around 0.275 joules. The kinetic energy, which is the green squares, and the potential energy, which is the orange triangles, appear to be inverses of each other. When you add the potential and kinetic energies together, they add to be equal to the mechanical energy of the rebounded ball. After the ball rebounds again, it loses some of its mechanical energy through the transference of heat to the floor, making the mechanical energy less than the rebound before it. The same pattern continues through the third bounce. The percent loss formula is expressed as shown as percent lost equals the first value minus the second value divided by the first value you had, and then all of that multiplied by 100 to give a percent. For our first impact, the initial mechanical energy was 2.7 or 0.27 joules, and the end value for it was 0.249 joules. So we had that. So we had 0.27 joules minus 0.249 joules divided by the 0.27 joules multiplied by 100 to give a 7.7% loss of mechanical energy. During the second impact, the initial value for mechanical energy was 0.114 joules, and the final value was 0.091 joules. So the 0.114 joules is subtracted by 0.091 joules and then divided by the 0.114 again and multiplied by 100 to give a 20.18% loss of mechanical energy. During the third impact, the initial mechanical energy is 0.1 joules, and the final mechanical energy is 0.71 joules or 0.071 joules. So the 0.1 joules is subtracted by 0.071 joules, and then divided by the 0.1 joules multiplied by 100 again to give a percent loss of 29% of the mechanical energy. The pattern that is shown in the data is that there is about a 10% increase in percent lost every single rebound of the ball. So the final percent lost is about 30% of the mechanical energy. Here is a visual representation of the percent loss of the mechanical energy over time. The very initial drop value of mechanical energy was about 0.375 joules. And as you can see, as time goes on, each tier of mechanical energy goes down after each rebound.
Now for the summary. The ball starts out from the drop point with the highest amount of potential and mechanical energy it will have throughout the trials. Once the ball is dropped and is falling through the air, the potential energy is converted into kinetic energy, while mechanical energy stays the same. The ball then hits the ground, which then absorbs energy from the impact and takes away some of its overall mechanical energy, around 10% each time. The ball keeps going through this energy cycle until the ball itself has no potential kinetic or mechanical energy left. When this occurs, the ball is stationary on the ground and has no energy left.